With depth, what does water salinity generally do? Increase or decrease? Increase. In fact, water salinity, if you actually do some analyses, the salinity of water at depth in the earth, especially under high temperatures, can be up to 10 times higher than what it is in seawater. Okay, that's an important consideration. It changes the density and all of the water, and it changes the behavior, how the water actually will deal with the rocks, etc. What are spatial arrangements of organic compounds called? Isomers. The isomer series, alkanes, alkenes, polyaromatic compounds. And if you're wondering why in God's name are we talking about organic chemistry in a geology class, it's because ultimately you have to understand what you're after in petroleum. So yeah, you have to do an awful lot of organic chemistry. I don't know. I don't think it's going to be enough to save you from a terrible final exam, but I'll think about it. API stands for American Petroleum Institute. API units deal with what? More, I think it's probably, it depends on how you look at this. It's got to be viewed as density, viscosity. It's basically the fluid nature of the petroleum you're after. And again, this is something you have to be aware of, because if you're looking for a sweet crude oil, by definition, a sweet crude is something that flows really easily. It's easy to get out of the ground. It's a lot less technological issues than if you're dealing with something that is a heavy crude oil or a tarry type substance. And indeed, this is something, I mean, if you guys get in the petroleum industry, drilling in the Gulf Coast is wonderful until a well goes bad. But that's a mixed curse if you think about it. Had that oil not been sweet crude, if it were tarry, it would have been self-sealing. It would have frozen solid in the hole, never would have been a problem. But consider yourself this. What if you have oil that has a very high API, turns to tar the minute it gets below the temperature of the reservoir, say 200 degrees Celsius? How do you get that from the bottom of a hole through potentially 5,000 meters of cold water up to the surface of a ship or to a pipeline? How do you keep it fluid as you go from one place to another? Have you ever thought about that? How do you get Alaskan crude and bring it from the reservoirs down to Valdez where they can export it in ships? They have to keep it heated. Who pays for that? How does it? You get the idea now that the costs are incredible. So if you're going to be trying to get a well drilled and you've got to keep the damn pipe heated, you better make sure there's enough oil to actually pay for the heating as well as make you a little profit. So it's an important consideration. Of type 1, type 2, and type 3, which is the worst kerogen for petroleum? What does type 3 normally give you? Natural gas. And where does it come from primarily? What are type 3 kerogens? Terrestrial plants primarily and all. And what form of primary migration, this is the worst question of them all, by the way, this is a real hard one to word, is responsible for transport of petroleum out of muddy source rocks? Liquid migration. Basically, it comes out as a liquid. And the whole purpose of that was, and this is an important consideration too. We've talked about this. If you've had me in any class before, I get excited when people start talking about oil, the relationship of reservoir rocks, source rocks, and cap rocks, or trapping mechanisms and all. And I always tell you that you have a source rock. That's where the oil forms. But we never, ever, ever talk about how you get oil out of a tight black shale into the reservoir. All right? And the question is, how do you get that? And there's been a lot of study on this, because knowing how you get primary migration, that's what primary migration is all about, tells you something about where to look for the oil in the first place. Getting it into the reservoirs and moving it from one reservoir to another is a piece of cake compared to how you get it out of the source rocks to start with. Okay? So that's an issue that we need to consider as well. All right, now a couple things before we get started today. Tomorrow is your lab. It's going to be a mixed bag lab. I haven't talked to Connors yet about what he wants you to do with those numbers you measured last week. We'll figure out something to do with that. I have some mathematical stuff that you guys need to do for me, as well as doing some microscopy. Now, all of those things, all three components, are way too little to run in a single lab. In fact, the reservoir characterization lab was always meant to be kind of like a filler lab anyway. So you'll have plenty of time to get most of that done in the lab setting tomorrow. Make sure you bring a calculator with you. You are going to need it, okay? And if you run out of time, the calculations can be done at home with no problem whatsoever. But we have another complication. We have the euchre presentations tomorrow. Now we have at least 2 people in this group that are in euchre, right? Who's doing euchre presentations? 2 of you, okay? You guys have to go to the presentation. Those of you that want to go and support your colleagues at euchre, I would encourage it, but you guys have a window of 30 minutes. You go there, you give them support, you say how wonderful it is, and then you come back. This is not a free card to walk away, okay? We need this lab period. So if you want to go to euchre, you can go. What's the best time to go? Around 2:30, is it? 2:30 to 3 o'clock? All right, you'll have from 2:30 to 3 o'clock to go to the euchre presentations, then you come back for another 50 minutes of time in the lab. All right, that's the deal I make for you. But you guys have to be there when you have to be there, and you got to make up the work a little bit later on. Any questions? Okay, you can turn that off, have a seat, and we'll get started with today's lecture. Thank you, and you know what? Pull the plug, because it's going to start beeping again on us if we're not careful. Coffee. You know, I miss my old 302 group, of which half of you were here, because I'd come into the 302 class and be a pot of coffee waiting, and I don't see, is coffee, is it warm there? When was it made? This morning, like how many minutes ago?
Like an hour ago. It's extra bowls. You may not be on the
Okay, hour ago is okay. I approve of that. The only thing that's a real pain in the ass is having to have the coffee pot back there, because we keep blowing circuits here. Is that what the problem is? Yeah. Okay, that's light. All right, actually this is lecture number 4. It should be petroleum part 2, not petroleum part 1. Today what we're going to do is carry on with our introduction to how petroleum actually works. This will be the last time that we talk about stuff that is specific about petroleum formation and migration. And again, the reason why we're doing this is so you have some familiarization with how oil gets around in the rocks. Starting on next week's lecture on Monday, we'll start talking about geophysical techniques as used in the petroleum industry, starting with electric logs, starting with SP logs. But for today, we're going to finish off talking about petroleum. Last time, the online lecture, just a reminder for those of you who saw this, and this, as I understand it, many of you just saw this lecture about 10 minutes ago, so this should actually be quite familiar to you. We talked about petroleum in general. We talked about subsurface fluids, the origin of petroleum, and the migration of petroleum, at least the primary migration of petroleum. A couple things to note. We talk about oil, that's what we're all after, but water in some cases is as important as petroleum and natural gases, because water is the major fluid that we have in the subsurface. It is water that is responsible for pressurizing, in many cases, reservoirs. It exerts a pore pressure, and by looking at how water actually is involved in the reservoir production, it's going to tell us an awful lot about how petroleum actually works too. Your theory about me having a boring enough voice to put your kid to sleep has failed. Dana was telling me earlier that she's watching the videos and the kid is just going like falling asleep. So I was hoping I could actually start marketing my videos to maybe baby Einstein as a sure sleep method. Introduction to petroleum. By definitions, we're talking about petroleum including basically all the liquids, all of the semi-solids, and there's awful lot of stuff that is not exactly liquid in petroleum, and gases and solutions of these components. And of course from this we divide it up into different divisions. Crude oil, which is what we're mostly after, is a substance that's got an awful lot of solid material in it. After you more or less refine it or distill it, you've got to treat the residue as a toxic material and get rid of it or burn it off, as is often done in refineries. And gas condensate is basically the lightest components of stuff. That's the stuff that comes off. They actually get a lot of gas condensate off of natural gas wells. It comes up as a liquid. They do collect it because it actually is well worth refining, because you get basically 100% recovery in terms of useful products on that. And how many of you were impressed by this picture? You know, it's an interesting way to deal with crude oil. I'm not sure about this substance. Crude oil, I mean, I would not want to get in contact with it. It's got a lot of nasty stuff in it, including those polyaromatic compounds, benzenes, toluene, and all, which are known carcinogenics. So I'm not sure if I would be smiling as much as this guy seems to be smiling. Characterization of the organic compounds. The interesting, and this is still kind of freaky to me actually, is the fact that you end up having basically the same ratios of carbon to hydrogen to the other components, the nitrogen sulfide, sulfur and oxygen compounds, regardless of the nature of the oil you get. I suppose this has something to do with the breakdown of the original ingredients. And if you consider that most oil, regardless of how it actually turns into the different types of series you get, it starts off from the same organic material. So I guess you've got the same starting block. But I would have thought that in some cases there may be some diagenetic reactions that cause things to be lost. Maybe like the sulfur combining with the hydrogen or something, giving you some sort of loss in that case, but apparently not. Anyway, we use the ever popular ternary classification scheme for classifying the oils, and there are the different series that you get. And here again was the different grades of petroleum. And this is important. In fact, of all the organic chemistry, petroleum geologists have to understand this is the one that is most important because it tells you something about the nature of production. Now, while it's true that most of the production component is going to be coming from the geoengineers, understanding what you're dealing with is going to be important because a lot of times if you're trying to sell a new well or a new play, because remember, the more you can sell your ideas, the more likely you are to actually get an oil well in, and that allows you to advance, you become more successful. If you're dealing with something that is going to have, let's say, a heavier API content to it, you want to find a place where you can actually come up with different types of drilling techniques. For example, maybe doing lateral drilling or fracking it. Fracking will cause localized breaking of the rocks to increase the amount of local porosity to get more oil into it and also. And there's the three types of kerogens: type 1 kerogen, type 2 kerogen, type 3 kerogen. It depends on where stuff is or where it comes from in terms of origins. Okay, so ideally type 1 kerogen is the one that gives us a really good source for oil and natural gas, whereas type 3 kerogens, which come from terrestrial materials, tend to be a little bit more likely to give you natural gas. This is where the coals basically come from. It all has to do with the hydrogen-carbon ratios. And the general argument is the more or the higher the carbon ratio you got, the more likely it's going to give you the coal fraction or the natural gas fraction. Organic maturity, this is another consideration. And again, this is really quite important too, because if you're looking for potential places for oil, if you're developing an oil field, it's not an issue because you know where the petroleum window is. But if you're in a new area, you have to get an idea of things like the geothermal gradient. And there are different areas where the geothermal gradient is higher, which means your level of maturation is going to be closer to the surface. For example, California, off the coast of Los Angeles and various other places, they've had a pretty major oil industry there since the early 1900s. In fact, if you think of many of the oil companies we have in the United States, Caltech, for example, Esso, a lot of those things actually were first started in California. Okay, so they ultimately became things like Texaco and ExxonMobil, etc. And the reason why they had actually pretty good success in the beginning was that there's a higher geothermal gradient in that area. So they only have to go down a few thousand feet to get pretty good recovery of petroleum. Where we are here, though, because we're in more of a stable continental area, our petroleum window is well down below about 5,000 feet. So 5,000 to 12,000 feet approximately is where we have our petroleum window here. And again, this is an important diagram because it shows you how the petroleum window is essentially dealing with temperature, and where that actually is depends upon what the geothermal gradient actually is going to be. So this is a good, a nice, simple diagram by which to explain things. And by the way, I didn't mention this in the online video, but I perhaps should do this here. You're going to see this biogenic methane component. That's the stuff that is being produced by degradation or anaerobic reduction of organic material by bacteria in the surface. Okay, so this is the interval where you're actually having diagenetic processes, where organic material is being broken down to give you methane. But you see it kicks off fairly soon, and then what happens is you get more into the burial window, where the biology is not going to be as good at breaking down things, less bacteria, in other words, below the surface. Did you have a question?
What is the lighter area? What does that represent? Nothing?
I'm sorry, this area here? Yeah, that's just the other side of the diagram, and also it's telling you percentages, and also it's not a 0 to 100% graph. It's just basically showing you the percentages of methane being produced from stuff. So All right, now here's our goal for today. We're going to talk some more about migration of petroleum, but this time we're going to be talking about migration in terms of secondary migration. Secondary migration is where you basically now have the oil out of the source rock, and now you're trying to get it into what we will eventually call a reservoir rock. We're going to be talking about reservoirs, the types that we have. We're going to talk about a couple trapping mechanisms, and all these things are going to be done in a series of just cartoons, not many of them as it turns out. And then lastly, we're going to be talking about porosity. And porosity, as you should already know, is the amount of holes that you have in a rock. But there are different types of porosity. And again, here you have to appreciate that the type of porosity is going to control the potential that you have for a reservoir. It's going to control the likelihood that oil is going to be able to be economically recovered from a reservoir. And it's one of the things that all geologists have to have a fundamental understanding. Know the target that you're going for. If you're looking for a limestone as a reservoir rock, a limestone is going to be potentially very different in terms of the porosity than a sandstone or a broken up basalt or something else that has the potential to be a reservoir. Okay, so we have to talk about the different types of porosity, and indeed that's what part of tomorrow's lab is going to be about. You're going to look at a couple thin sections and try to get an idea of what kind of porosity you're actually dealing with under those thin sections. Okay, so this is a leftover slide, basically from what we were dealing with in Monday's online lecture. It was our introduction to petroleum migration, and it talks about this type of diagram. This is the classic get-to-know petroleum type of diagram where you have accumulation in structural traps in this case. Talking about primary migration. Primary migration is where you are actually getting material coming out from the source rock. And this was actually, many of you are probably thinking, why are we talking so much about this, especially since most of the ideas that have been suggested don't seem to actually work. But it's one of those mysteries now that still is not really well understood. How do you get oil out of a source rock? And the general consensus is that most of the oil coming out of the source rock is probably coming out already in a liquid form. It doesn't seem to be able to diffuse. It doesn't seem to be able to come through from osmosis, not colloidal transport. It's not coming out dissolved in gas. That was a popular idea for a while, incidentally, because the gas was thought to be able to move through the shale a little bit better. And if you could dissolve the petroleum in the gas, that would be an effective way of getting it through. But, of course, no one's been able to demonstrate that happening. So the general consensus now is that you end up getting these so-called microfractures. And liquids, at least water, has demonstrated time and time again that it is capable of flowing along fractures that are only on the order of maybe 100 nanometers across. A nanometer is a very, very small fracture. And under those levels of things, I mean, all rocks are ultimately going to be fractured up. So the idea now is that the organic material is turning into a liquid, starts to migrate along all of these little microfractures, and at the top of where the source rock is, all this oil is slowly going to be dripping out as small little droplets everywhere along the surface. And given time, those drops will start to accumulate and build up and ultimately travel somewhere. So primary migration, the stuff that takes it from the source rock into the initial reservoir, or at least the pathways where the reservoirs can be encountered, is probably caused by the same form of migration that secondary processes are all about. Okay? Now, about those secondary processes, which we're going to get to in a second, we should first of all talk a little bit about what reservoirs are in general. The term reservoir is reserved, or is used whenever we're talking about some sort of a rock that is a storage facility for some sort of fluid. Now, when we're talking about petroleum, obviously those fluids are going to be petroleum and natural gas. But the reservoirs also contain abundances of water, and in some cases other fluids too, like hydrothermal fluids, which, you know, in some cases are so saline this hardly fits the definition of water at all. Okay? Most reservoirs are sedimentary in nature for blatantly obvious reasons. If the source rock is going to be sedimentary, then you're already going to be in a sedimentary province. And therefore, the reservoirs are going to be largely sedimentary as well. However, every once in a while, somebody will experiment and find a reservoir that nobody ever anticipated. In fact, the Russians have been remarkably good at doing this. They find reservoirs in granites. Now, how the hell you get oil into a granite, I haven't got a clue. But the granites are almost always fractured up. They got joints in them. And one assumes that the oil is migrating laterally and encounters maybe some sort of an uplifted basement rock area where the oil can get into it and starts to more or less get trapped by unconformities that are at the top of the granite. The Russians, however, have come up with a completely different explanation for this. And I'm not sure how pervasive this idea is, because it really is kind of bizarre. They've come to the belief that an awful lot of petroleum, particularly the natural gas components, is not organic in nature in the first place. They have argued that natural gas is a mantle-related material, and it's working its way up through the asthenosphere, getting trapped in the granites. That is not a particularly well-received idea. However, we do know that there is significant amounts of natural gas in the mantle because it's how diamonds form. All right? I don't know how you get liquid petroleum from that type of idea, nor do I know if the Russians have actually done any legitimate geochemistry work, because you can figure out where carbon comes from by looking at the isotopic signatures of things. We can very quickly determine which carbon has come from a volcano, which carbon has come from organic material. And I've not pursued this enough to figure out if they've actually done any numbers like that. Personally, I can't think of a mechanism whereby you can get petroleum and natural gas in abundance without having some sort of a biological process involved in it. Oops. The sedimentary rocks, at least the reservoirs, what will count as a reservoir, has to be both porous and permeable. Now, we don't have to go into detail about this because I think almost all of you have had you had conors at the beginning of this, so you know that that's one of the major things that's important for aquifers as well. So you know that this is a requirement for all rocks that are going to be hosts of fluids. What we're going to be doing, however, is looking at the types of porosities and permeabilities that are associated with deeper components of the geological column, and deeper meaning within the petroleum window. The trapping mechanisms come in many, many, many different varieties, okay, or if you wish, many different flavors. They can be stratigraphic in nature or structural in nature, or, as you'll see in a few minutes, a lot of other things. Now, the diagrams you see here, which are available online now for you to download when you want to, give you an idea of some of the different types of trapping mechanisms that have been observed and have been drilled into. Now, remember, these are idealistic things, okay, and it should be blatantly obvious to all of you that there's nowhere in the world, that I know of anyway, where you're going to be able to drill a hole and find a cave at the top of an anticline that is full of water. What this is showing you is where it's full of oil. What this is showing you is where you're likely to find oil concentrated within pores within what are obviously reservoirs. So you can have structural things that involve either simple folds or a combination of folds and faults. These are actually really quite good trapping mechanisms. What the fault does is it takes your reservoir, splits it, and part of the reservoir now comes in contact with part of rocks that have no porosity and permeability. So it's a very effective trapping mechanism. Although you can lose an awful lot of petroleum along the fractures and faults going up to the surface. So not all faults do this. Some faults actually are responsible for draining a reservoir. And if you lose all your oil because it all seeps up to the surface, you don't have an oil well. You don't have a reservoir. What you have is a surface oil seep. And indeed, one of the things we used to do when people were first looking for potential oil and gas reservoirs back in the late 1800s and early 1900s, they didn't start randomly drilling everywhere. We didn't have really effective geophysical techniques at that time. What they did was wander around the countryside, and if they saw oil seeping at the surface, or in many cases, natural gas flaring off at the surface. We used to have a natural gas flare in Mobile, for example, in I think it was the 1800s, burning at the surface. They got the idea that there was the potential for petroleum below the surface. I mean, that's not particularly clever thinking. That's just blatantly obvious. So that's where they would start to drill. And the argument was, if you have oil and gas leaking at the surface, there must be potentially a reservoir just below the surface. Now, of course, we're not going to find that very often. Salt diapirs are very effective trapping mechanisms. They're effective in two ways. Number one, they push up the rocks They cause localized anticlines above where the salt diapir is. They also cause the rocks that they're penetrating through to curve upwards. Salt diapirs are not like plutons that are hot, that burn their way up. These things push their way up, and as they go, they drag the sedimentary rock layers with them, and that causes all sorts of nice little traps along the flanges, as well as at the very top. It's at the very top where you get interactions between groundwater, you get dissolution, secondary mineralization, sulfur and hydrite can form these environments. You get a lot of pockets, and here you do get the potentials from some fairly significant caves, if you wish, and oil can concentrate there as well. Traps can also be stratigraphic in nature. Stratigraphic traps are those that are associated with some changes, lateral changes in the rocks. For example, classic pinch-outs. Perhaps you have some sort of a topographic difference in the stratigraphic units. For example, if you have a series of barrier islands that comprise a formation, classic example of that is the Norphlet Formation around here, which is deposited as a series of barrier islands. There will be local highs and local lows. Along the edges, you could have potentially fine-grained sediment that would be a good trapping mechanism or seal, in which case you can get some nice little bumpy bits. And of course, the classic example of this type of mechanism is what you get in a reef, where a reef gives you a localized high of very porous limestones, and on either side of it you can get it buried in very, very fine-grained materials as well. And then there's the combination of them where you actually have some stratigraphy that is also linked to structure. For example, unconformities are very good things to look for. Now, all of these trapping mechanisms are really, really, really easy to spot using geophysical techniques if they are big enough. So if someone finds what they think is a salt diapir below the surface because there's a seismic line that goes across it and shows you something, I can guarantee you they're going to drill through it. But a lot of these traps, especially these, are a lot harder to identify because you're talking about rock units that might only be on the order of 50 feet thick, and the resolution of some of these seismic lines might only be 100 feet, which means you miss them. So it gets to be difficult to find small-scale things like this. And the small-scale traps like this are still really quite effective. Because if you've got a rock unit that might go for, in the subsurface, maybe over 500 square miles, which isn't very big, pinches up, or pinches out up dip, you have the potential to have a sheet reservoir that if you can tap it in a couple places, is draining an area that's got more oil in it than you would ever imagine. And yet you can't spot it easily on a seismic line. So that's some of the perils you have to deal with. There's also sedimentary ones, and these are the components that are incredibly tricky to identify, that sedimentologists have really changed the profession over to help to enhance their potential for recovery. In cases like this, we can have facies changes. Most of you have not taken sedimentary petrology yet, so you don't know what a facies change is, but a facies change is where you actually have a lateral change. You might go from a sandy unit into a muddy unit, not as a pinch-out, but just in terms of a lateral gradation. That still can give you a pretty effective potential for an oil reservoir. And also we have a lot of these things that are associated with sea level changes, and this is what's going to more or less dominate about the last third of my component of this course, is talking about sequence stratigraphy, the effects of sea level change on how sediments are deposited. Because you can get some very sudden steps where you can have sediments being deposited at this level which are very porous and permeable. A sea level change will cause them to suddenly have that entire area of sedimentation shifted either inwards towards what would have been the shoreline and into deeper water, trapping those bodies temporarily until the next phase of sedimentation covers them up in something else. So you get these sudden potential traps caused by sea level change, which is the reason why so many sedimentologists now deal with sequence stratigraphy and sea level change on a regular basis. And of course you can have any one of these combinations, okay? So you get the idea. It just goes on and on and on. The trapping mechanism is, of course, incredibly important. So if you have your reservoir, you still need to have a means by which to make sure the oil gets concentrated in a certain area. Porosity. Porosity also comes in a bunch of different varieties. In fact, more varieties than you're actually going to see here. Okay, this is one of the things that if you're working in an oil company somewhere, you normally have somebody who's the resident expert on the reservoir characterization. That would include trying to determine what kind of porosity you've got, what kind of permeability you've got. They deal with actual hard specimens. There are ways to get samples from the subsurface. You can get cores. You'll see some cores in this class a little bit later on. You can get cuttings. You'll see some cuttings in this class a little bit later on. And you can also get samples through some of the different types of logging devices that we use. Any way you want to look at it, there are times when you need to see what the rocks look like, even if they are 15 or 20,000 feet below the surface. When you do that, you can start studying it, getting the porosity measurements, getting the permeability measurements out of it, and of course making thin sections to get an idea of what is actually making up the rocks. If you were to do that, you would find that that porosity comes in 2 or 3 different major varieties. There's 2 that we're talking about here. Primary porosity is that porosity that is associated with initial deposition or is left over from depositional processes. It includes interparticle porosity, which means the whole space that is between the particles. Framework porosity, which again is kind of like the holes between the particles, but has to deal more with larger components. There's fenestral porosity, there's intergranular porosity, there's a whole bunch of different types of porosities. I will show you some pictures of these in just a second. And then we have secondary porosity. Secondary porosity is the porosity that occurs after deposition is over. Again, if you have taken sedimentary petrology, you know that this is what we would call the diagenetic processes. Secondary porosity can involve dissolution. If you're dealing with a limestone, this is a major component of it because some chemical phases are more likely to dissolve than others are. So you can get ooids that dissolve out, leaving you with, I kid you not, molded porosity. You can get molds of shells. You can get bugs. You can get all manner of stuff. Some of these holes can be huge. And I told you that there's no such thing as oil forming in a cave underground. But I've seen some holes in rocks that may not be a cave that you and I could get through. But holes like this that are extensive and connect with other caverns this big can contain a huge amount of oil and natural gas. If you're talking about a rock body that is 150 feet thick, that covers half the state of Texas. Okay, so understanding these things is really kind of important. And then we get into secondary dissolution, etc. Okay, now I could list up a zillion of these things here, but probably the most effective way of showing you what porosity is all about is to actually show you what these things really look like. So here is a thin section, and I think, is there anybody in this class who's not had a chance to look at the microscopes before? Either in petrology or in SED or in mineralogy? So all of you have looked down a microscope before. You more or less know what you're looking at. If you haven't seen a sedimentary rock under a microscope before, here's your first one. What you're looking at are 2 images. This one is in plain polarized light. This one is in crossed nickels, and I did this entirely or only so that you could actually see the grain boundaries are all sutured together here entirely. Both of these rocks are quartz arenite sandstones. This one, classic beach type rock. This one, believe it or not, also a classic beach type rock. Okay? Here what you're looking at are grains indicated by this yellowish color in through here, and between it you see this bluish gray coloration. That's artificially stained porosity. This is a rock that has very little cement in it. There's just enough cement to glue all the grains together. It's what we call a friable sandstone. So everything, you can pick it up like this and start breaking it apart in your fingers. But underground, this is a classic reservoir rock because that's all the void space that you see here. This rock has 40% porosity in it. It probably has enough permeability in it to make it both an excellent oil reservoir if it had oil in it, or a water reservoir in it if it had water in it. This rock, on the other hand, all the quartz grains here are fused together. This is what happens when you either have metamorphism, where the rock is actually squeezed and the grains get pushed together through a process called pressure solution, or in some cases, this could be simply a quartz cement that is just filled in all the surrounding area. Gut feeling on this one is that this has been metamorphically altered, or at least pressure altered. See how the grains are all kind of sutured together? That's not normally what you would get if you were dealing with a rock that was just cemented. Doesn't matter its origin. The things you're looking at here is a porous sandstone, good. A non-porous sandstone, not so good, unless your intent is to more or less make quartz sandstone countertops. That would be good for that purposes, but not if you're looking for oil and natural gas. So ultimately, what we want to do now is look at all the different types of porosity that is available. And we'll start off with the primary types of porosity, okay? This is an example of primary porosity. It's also called interparticle because it is the porosity that occurs between particles. All right, that's the classic porosity that most of us think of. The diagram you see here now is a summary of all the major types of porosity that we recognize in sedimentary rocks as related to the petroleum industry. So here's your interparticle porosity. That is basically ooids, but you can see that these things are the same, okay? The space between the grains, if it is preserved as open space, makes for the potential of a very good reservoir. Provided, of course, that the sediment was capable of having a lot of space between it in the first place. All right, so again, those of you that have had said before, you know that some sandstones are very well sorted, like this one is. Other sandstones, not so well sorted. If you have a lot of small particles as well as large particles, the small particles tend to fill in the pore spaces. Net result is a poorly sorted sandstone generally has less porosity, less permeability. So ideally, you look for those sandstones that are likely to have high amounts of porosity, which again are sandstones that are normally associated with beachy type environments or high currents. No wonder then that if you are a sedimentologist working for an oil company, you get really excited if you find what you think is a beach deposit at 10,000 feet below the surface of the earth. Or if you find what you think are point bars associated with a river that might be at 8,000 feet below the surface. By the way, point bars and rivers are particularly good because they have this tendency to twist around, bend around, and suddenly stop if there's a cutoff, giving you all sorts of classic trapping mechanisms. So rivers are great things to go looking for. All right, so primary interparticular porosity looks like that. Then we also have primary intraparticular porosity. Intra means within the particles. Never, ever, ever, ever underestimate the ability for the grains themselves to contain a lot of holes in them. This is an example of the type of stuff we're talking about here. These are foraminifera, very large foraminifera, and incidentally these are basically almost live foraminifera. I mean, I picked these things off the beach in Australia, made a thin section to see what they look like. But there are plenty of rocks that contain biogenic components that have holes within the grains. And again, if you have paleontology, you know what I'm talking about. Bryozoans are full of holes. Corals are full of holes. If you have a rock that is full of corals, even if the corals get tightly cemented together into a limestone, there's still the potential for an awful lot of holes within the particles themselves. But the more cement you have, the more likelihood those holes become isolated. And if they become isolated, you lose your permeability. What happens to your potential for a reservoir rock? Starts to drop down a little bit, okay? So intraparticular porosity is important as a primary porosity, but not necessarily for preserving or making it possible to get oil out of the ground. Here's some more intraparticular porosity, and I call this primary, although it's really debatable. This is a fascinating variety of it. See this grain here? That grain there? Both of those have a significant amount of blue in them. The blue is hole space. So you get the idea right away that some of these grains themselves have holes in them. But notice the pattern. Does that look anything like a biogenic pattern? Does it look anything like the spirals you see in the forams here? In fact, does that resemble any type of biogenic structure you've seen in a paleontology class anywhere? It shouldn't. I mean, if you were to say, I don't know, then I would immediately give you some additional information about this particular slide. This is a siliciclastic rock. There are no carbonate components in it as well, at all. There are no things in here that were once living organisms. In fact, this is an immature siliciclastic sedimentary rock. Someone remind me what an immature siliciclastic sedimentary rock contains. What does immature mean? Not entirely quartz. Well, if it's not entirely quartz, what does it have in it? Feldspars, biotite, all manner of stuff. In fact, you can tell that this is a mixture of all different types of rocks. This is quartz, this is probably iron oxides, etc. These grains here are probably feldspars. What's happening to the feldspars? Very good. If you remember anything about weathering cycles from Geology 111, you know that feldspars are unstable at the surface of the Earth. All right, and over time they break down into kaolinite and clay minerals. You know, we seem to forget that that process is not limited by being at the surface of the Earth. If you have a siliciclastic rock that has water flowing through it below the surface of the Earth, the water is going to continue to carry on with the reaction. So the feldspars, even if they manage to survive, to be transported somewhere and be deposited, may not survive the alteration that takes place afterwards, which means they can break down in place. And that's exactly what's happening here. What you're looking at is the remains of some of the cleavage of the feldspars, and now you don't see an awful lot of clay in this because the clay has probably been removed, possibly dissolved out by the very fluids that are actually causing this alteration. But consider a rock that's got a lot of feldspar in it. If you can alter the feldspar, get rid of the clays, you're left with a rock that's got a significant amount of porosity in it. Now, I don't absolutely know why I've classified this as primary, because it's not really primary. It takes place after the fact. But it is certainly locked into the depositional fabric, and it is certainly within the grains. There's a mixed blessing in this, and I have to tell you about this a story of one of my clever colleagues. He graduated from my same undergraduate school 1 year before me, and he went on to work at the same oil company I was at. He became somewhat of a god there because he solved a problem. Here was a student right out of undergraduate degree working for a major oil company in their research division, and I have a funny feeling that someone walked into his office and just basically put something on his desk and said, "We got a problem, see if you can figure it out, young kid, young Turk." And he looked at it and he figured it out. Here's what the problem was. This company had drilled into an area that had a lot of oil. They had already started drilling the area. They were getting oil out of it. They were expanding the reservoir. But every time they drilled into the damn place, they got off with an initial amount of oil, but then the flow dropped remarkably fast. Far too fast to be explained by normal processes. They didn't know what was going on. Now, this person, I'm not going to give his name in case he happens to see this video and I forget it wrong and all, but his name, we'll call him Dan. Dan got some sections, looked at it, made some thin sections, got his microscope out, and saw that it was a rock that looked very much like this, full of feldspars. But unlike this rock, the clays didn't migrate. The clays were actually where the feldspars were. The feldspars had been completely broken down. The rock was full of clay, and the clay was concentrated within the grain boundaries of the original feldspars. So he thought about it, and he said, you know, when you make an oil well, what you end up doing, you're drilling down into the field, right? And when you get into it, you have to kind of purge a little bit of the mud away from things. So they often over-pressurize things. They push water into the reservoir. And then that's not a problem because it then comes back up as you start extracting oil from it. The oil pushes it out. Well, what they were inadvertently doing this time was they were forcing the clays that had been trapped within the grains into the pore space. They were killing the reservoir by drilling using the water. So I never actually saw what happened with this, but I like the idea that, you know, he walked into this guy's office maybe a week later and said, well, here's the problem. What you need to do is drill and use this fluid instead. Whatever he recommended, they got all those wells to work, and he became a hero based upon analyzing this. Had nothing to do with locating where to drill, had everything to do with knowing your reservoir. So it's important. Well, once again, during the lecture today, I ran out of time. I really have to learn to pace myself a little bit better than I've been doing so far. So I'm recording some additional notes in my office. What you're looking at here is an additional type of primary porosity. This is called fenestral porosity. Fenestrae are very thin, horizontally layered or horizontally oriented void spaces that are normally found in tidal flat environments. Essentially what happens is you have organic material that starts to decay after burial, and when the organic stuff produces gases like methane, or in some cases carbon dioxide, it will tend to exert a gas pressure that will keep some of the layers open a little bit longer than you normally would expect. Basically what you end up getting are very flat, horizontally spaced voids that can be a form of pretty good porosity in rocks that you would otherwise not expect to see porosity in. This particular image is not particularly easy to recognize the fenestrae. They are the lighter areas. It's dolostone, which is a common type of rock where tidal flat sedimentation takes place. So basically what you have is a very tight dolostone with these fenestrae that are kind of spaced between them all. So it's associated with, in some cases, source rock, and it is a common porosity in sequences that are deposited in very shallow marine types of environments, or, as I said earlier, tidal flat environments. The slide you're seeing here now takes us into the secondary types of porosity. This type of secondary porosity, or secondary porosities in general, are porosities that are not necessarily associated with original depositional fabrics, but are the result of processes that occur after deposition. In this way, they're referred to as diagenetic processes. Diagenesis refers to all changes that have occurred to a rock, sedimentary rocks anyway, after their initial phase of deposition is over. Now, what you're looking at here is a couple of shells, probably bivalves, that have started to dissolve out. Now, they were originally composed of probably aragonite or calcite. And what happened was, because aragonite is relatively unstable given meteoric conditions, those particular materials start to dissolve. Calcite can dissolve out too if the conditions are right. And if you're in a rock like a dolostone, as this rock is here, the carbonate components, calcium carbonate components, tend to be much more soluble. So given the right circumstances, they will preferentially dissolve. Now, this particular slide you're seeing here is a little bit more complex than simply having the shells dissolve out. What happened was the shells were dissolved out entirely, and now you have a secondary phase of calcite starting to fill the void spaces back in. Now, that may sound complex. Carbonate rocks, limestones and dolostones, tend to suffer from fairly detailed and highly variable changes. So this is not all that complex as far as carbonate diagenesis goes, but perhaps at this level it may be something that's a little bit unwelcome to you. The main thing to note here is that there's still a significant amount of areas of blue, which indicates that there is a significant amount of porosity available here. And if you have a rock that's got enough shells in it, if all the shells dissolve out, then you can have effective porosities exceeding 40 or 45%. So not a bad type of porosity to have, especially given that many of the reservoir rocks that we have are limestone, so they will be full of shells and things in them anyway. Here's another shot. This is actually one of my thin sections from my PhD research when I was working in New Zealand. And what you're looking at here is a cold water limestone that is composed of a whole bunch of different allochems, or different types of carbonate grains. Again, people who have taken sedimentary petrology might recognize brachiopods and bryozoans and a few other things. For the rest of you, you'll get that when you get into sedimentary petrology, but now just concentrate on the areas of blue. If you look, you're going to see an awful lot of areas of blue in here. That is implying that there's a significant amount of porosity in this rock. But if you look at it, you're going to see that most of those void spaces seem to be shaped with convex and concave curves to them. That's because most of these things are where shells used to be, and the shells have entirely dissolved out. In this case, you're looking at a rock that has got incredible amounts of porosity, incredible amounts of permeability, and had this formed in an environment where oil might have been able to migrate into those void spaces, and we'd be in the money big time now, because this is an incredibly, potentially porous rock. Sadly, at least from the point of view of petroleum geology, this is a rock that's exposed at the surface of the Earth, where geologists like yours truly can take samples of it and make thin sections out of it. But as I said, this type of thing can also happen in the deep subsurface, where oil and various other pore fluids can fill in those void spaces. Oh, classic image. Now this is actually this is the really the only image that you've seen so far that's not one of mine. This is a kind of a pixelated view of a oolitic limestone. And for those of you who don't remember ooids, ooids are those tropical carbonate grains that are formed from inorganic precipitation in a wave-agitated environment. So basically, it's the snowball type of grains. They're composed of aragonite. And once they are cemented together to form oolitic limestones, sometimes the aragonite that makes up the ooids dissolves out and leaving you holes. So what you're looking at here now is a pixelated view of some oomoldic porosity. And yes, the word oomoldic is a legitimate word. Basically, that means that the ooids have dissolved out, leaving these circular holes between the rest of the cemented rock. Now, ooids are tend to be very porous rocks initially, but they can get cemented very extensively too by other types of cements. So, oomoldic porosity, where the ooids themselves have dissolved out, is an important potential reservoir rock. But you also have to have the ooids actually connected together, and depending on what the amount of cement is, that may not actually occur. So you end up instead with a rock that resembles Swiss cheese. In other words, a rock that's got a lot of holes, but the holes aren't actually connected. And if the holes aren't connected together, then you're going to have a problem with actually having the oil migrate from one hole to another. Okay, so an interesting type of secondary porosity. Another very important type of secondary porosity is best referred to as fracture porosity. And what you're looking at here is a thin section. This is actually from the Cahaba River area. This Nuala limestone. Nuala limestone, which has some dolomitization in it. The dolomites are the what they look kind of cubic here, but they're actually rhombohedral. They're kind of colorless. Everything is stained in pink is calcite, and you'll see again the turquoise color. That is the void space cutting across both the limestone and the dolomite component of this rock. What you're looking at here is a fracture. Now this fracture is large enough that were you in an environment where petroleum could be produced, oil would be flowing along this thing remarkably rapidly. Fracture porosity is an important type of porosity in a lot of rocks. It's important in limestones, it's important in sandstones, it's even important in potential reservoir rocks like granites and basalts. And I mentioned this earlier during the lecture, that it may seem weird that a granite or a basalt could be an oil reservoir, and they're rare. But it's still possible to get them as being hosts for oil if they're broken up enough through fracturing to give rise to, fairly prominent types or fairly abundant porosity associated with the actual fractures themselves. And as I said, that does occur. Really, fractures are more important in more sedimentary rocks, though. All right, this is an image here. I believe this is the last one of the images for today's lecture. And what you're looking at here is best described as vuggy porosity. Vugs are as close to caves as we get at the microscopic to macroscopic scale that is provided to us by thin sections and basically hand specimen outcrop type of specimens. Vugs are large, primarily solution-induced holes that are largely interconnected that more or less affect limestones that have either a lot of materials in them that can easily dissolve out, or limestones that are subjected to an environment where there's significant amounts of groundwater that can flow through them, particularly if the groundwater is coming from various sources. We'll talk about the whole idea of mixed water solution when you get into sedimentary petrology and diagenesis a little bit later on. Suffice to say here that you can get a rock that has got an incredible amount of hole space in it. And again, if you look at this thin section here, you're probably looking at a total of 35 to 40% void space. And those voids, the individual vugs, are huge.
They cut across grains, they cut between grains. This indicates that this is largely the result of secondary processes. The rock had to have been cemented first before you ended up getting these super large void spaces cutting across it. So what you're looking at here, again, just to summarize at this point, is some of the major types of porosity that can occur in sedimentary rocks. And as I tried to allude to earlier, if you're going to be a competent petroleum geologist, you have to be aware of all aspects of petroleum geology. You have to be aware of how petroleum is formed. You have to be aware of how petroleum can migrate from the source rock into potential reservoir rocks. You have to be cognitive of the various types of holes that can exist in reservoir rocks, because, again, all these variables are going to give you an idea of the potential for developing oil or natural gas wells and an estimate of the amount of oil and natural gas that those reservoirs might in fact contain. Okay, so a little bit of knowledge about a lot of different things is really necessary in all aspects of geology. That includes the petroleum geology side of things. All right, so we're done now for today. Again, I'm sorry that this is, I had to record some additional information in my office a little bit later on. The nice thing about actually doing these lectures is that I get to add some additional stuff to them if I run out of time during the in-class component of the course. And hopefully this will not be a recurring thing, because I really don't want people to have to actually watch the videos to augment all their notes. This is more of a benefit for you when you're getting ready for studying, or if you happen to miss a class for a legitimate reason, because nobody would ever miss one of my classes because they want to bugger off and do nothing. Anyway, turning to stuff that's coming up now. Tomorrow's lab, that's Thursday, we're going to be doing our mathematical calculations. Please bring a calculator with you to class. You have some leftover stuff that Dr. Connors did with you out in the field last week too. I have yet, as I said in class, I have yet to actually contact him to find out what he wants to do with that. Hopefully I'll know by the time of lab tomorrow. We're also going to be doing a microscopy lab. We're going to be looking at some petrology, specifically porosity and thin sections. Coming up Monday, we turn to the real geophysical part of this course. We're going to start looking at SP logs. It's a variety of electric log. It stands for spontaneous potential. It's the first electric log that I ever had to use in my very brief career as a petroleum geologist. And so it's near and dear to my heart. And I'll go over what it's all about, how it works, and how it can be used for doing remote sensing in the interior of the Earth. Anyway, with that, we'll call it quits for tonight. And, well, I'll see you, I guess, in lab tomorrow. Ta-ta.